Start. And now our topic of discussion today is relations and functions. This is part 2 and part 1 is in the book 1. So how to deal with
Yeah.
this? So I'll just give the glimpse of what is a relation. So you might have forgot, but anyway, see, it's like suppose you have a set like A comma B, and there is another set, let us say 1 2. Okay, suppose I ask
Okay.
you to find A cross B, then it's very simple. You will write the ordered pairs A1 and
Yeah.
A2. I hope you remember this.
Yeah.
And
Yeah.
B1 comma B2. This is how we write. Okay,
Yeah.
this is how we write the ordered pairs. And now how the number of elements in the A cross B will be like the number of elements in A times number of elements in B. So that is n
B.
of A times n of B. Okay. So
Of
this
B.
is how one can compute the number of elements the in the relay in the
Relation.
I would say this is called Cartesian product. Okay, in the Cartesian product. And now what is a relation is it is a subset of this A cross B. It is a
Okay.
subset, one of the subset of this A cross B. This is what we have done earlier. Okay, and now
Yeah.
we'll go further. So it is a subset of A cross B. Now, okay. So here we go. So here A cross B are two sets. Then the relation R from set A to set B is a subset of A cross B. So that is called Cartesian product. This is most important. A cross B is not the relation. Actually, you will take the A cross B and then you take a subset of that A cross B, then it becomes a relation. And now if A comma B belongs to R, that means if it belongs to relation, then we'll write A R B. This is most important. A R B. That is A is related to B by the relation
AR.
R. If they doesn't belong, A is not related to B. As simple as that. And now, if n of A is equal to M, n of B is equal to n, then A cross B will have Mn ordered pairs. Therefore, total number of relations you can make from A to B will become 2 power Mn. So this is the concept what we have actually done. So how exactly it is 2 power Mn also I think I told you, but it's okay. I will tell you. Suppose it's simple only. So we'll see that why it is so. So that is based upon the binomial theorem. So I told you about the binomial theorem. So what does it says is that suppose you have the set A, which is containing, so it contains so many ordered pairs like x naught, y naught, x1,
Yeah.
y1, like this. So many ordered pairs. Of course, there are mn ordered pairs. And now there are the relations. This entire thing itself can be taken as a relation. Okay. And so choosing no element can also be a relation called an empty relation. There are mn ordered pairs like that. So you can write mnc0. That is choosing no element.
Okay.
Choosing one element, you can write mnc1. Choosing two elements, you can write mnc2 and so on. You will get
Okay.
mncmn. So the sum of the binomial coefficients, this is nothing but 2 power n. This we have solved in binomial theorem, so that we will get 2 power n. So this is how we can generate the answer. One can generate the answer like this. Okay. Now this is
Plus
the
M and
basic
C2.
fundamental idea. This is a very basic fundamental idea. And
Okay.
now there are some types of relations. This is like a notes, actually, I'll tell you. This is like complete notes kind of thing. A little bit boring, but we have to deal with this. But there are
Okay.
certain things you have to see. So with examples, we'll learn more, but we'll see what is There are types of relations. Something called reflexive, transitive, like that. Some names are there. We will see what are. So what is a reflexive relation? See, now let us see. A relation R on the set A is said to be reflexive if every element of A is related to itself. That is a beauty.
Okay.
Every element of A
is said to be reflexive in element of A related to
itself. What does it mean? It simply means that you get a doublet.
Double?
Doublet.
Doublet.
Find that in the ditro you say doublet, right? What is doublet? 1 1.
1 1. Okay.
If you have any such element available,
it's called reflexive
relation. Idea? You got the idea? Simple.
Okay, if it has
now
doublet,
doublet you need. For every element, you need a doublet.
Okay.
So if such thing is occurring, then you will say the relation is reflexive. Now let us check this. Now A is 1, 2, 3, they have taken, B is set. Then relation they have written 1, 1. It contains 2, 2. It contains 3, 3. Of course, they have written the other elements. Okay, 1, 3, 2, 1. Is a reflexive relation on A. Why it is using? It contains for 1, 1. All the elements of A which are present. It contains for every element, whatever you take. It contains the doublet. So you have the doublet 1, 1. The doublet again 2, 2. The doublet 3, 3. All the 3 are present. And that's why it's called a reflexive relation. Clear?
Okay.
It contains all the doublets. Now, you check this one. 1, 1 is there. 3, 3 is there. But 2, 2 is missing here in this one.
Yeah.
2,
and
2
it's 2, 1.
No, 2, 2 is missing. That's it. You forget about 2, 1.
Okay.
2, 2 doublet is there or not for every element.
Okay.
Is this clear? You just have to see. You see that 2, 2 does not belong to R. That's what he is telling. Doublet for 2 is missing. You forget about other elements. Doublet for 2 is missing. Forget. It is not. It is not reflexive relation. Clear?
But if it is, there is 2, 2.
Yeah. You see
and if there is 1, 2.
Doesn't matter, Aditi. You didn't get.
Then it's not a reflexive.
No, I didn't get you. I don't know. You had, suppose I say reflexive, you had, see the element. Okay, we'll take another example. No,
I understood like 2, 2, 3, 3. But then if there is 1, 1, 3, 3, 2, 2, and the last element is 2, 1, it's not a reflective relation.
I will ask you one thing. You just see this.
Okay.
So let us say this is A, B, C is there. And now I write the relation. Let us say A, B, B. I will write C. I will write the AB, BA, okay, and again C. Now, how do you check this is reflexive or not?
You first check if there are doublets for every element.
Every element of
A.
That's it. Every element of A, you just check the doublet. Whether it is present in the R. Is it there?
Okay.
Yes, it is there. Don't worry about other elements which are coming up.
Okay.
Understood?
Okay.
You don't have to check any other element. Whether for every element of A, whether you can see the doublet.
Okay.
Then it is reflexive.
Okay.
Clear? Am I clear this one?
Yeah.
Suppose I write some other relation R dash. Let us say A comma B. Double B. I'll write double C. Now whether it is reflexive.
AB, BB.
CC.
No.
No. Why? A
It
is
doesn't
not,
have A.
A doublet is not there. So it is
Okay.
not reflexive relation on A. Got it? No.
Okay.
It is not a
Yeah.
reflexive relation on A. That is how we will tell. Clear?
Yeah.
Yeah. Now, so this is where sometimes it's really confusing. So you don't have to check any other element. Check the doublets, whether for each corresponding element of A, whether you can find the doublets. Then only you will
Okay.
say that it's a reflexive relation. Because you see that next one, this 2 comma 2 is missing in R, so it's not a reflexive relation. Clear?
Okay.
Now, let's
Yeah.
move on. Let's move on. Symmetric relation. Now you see. A relation R in set to A is symmetric relation if A comma B belongs to R and then you topple that.
Okay.
So the toppled one, A comma B, when you topple that, what you become? What it will become? B comma A. Are you getting it?
Okay.
If you swap that, you will get B comma A. So after swapping, that swapped element also should be there in R.
Okay.
Okay. Got it? So after
Okay.
swapping also, that swapped element should be there in R. Then I will say it is called symmetric relation.
Okay.
Then it is a symmetric relation. Okay, right? So ARB implies BRA for all A comma belongs to A. Right? Got
Okay.
it?
So for example, A is
For example, you
1, 2,
see this
3.
one. A is 1, 2, 3, 4. And R1 and R2, two relations on A given by C. R1, let us see. 1 comma 3 is there. For 1 comma 3, where 3 comma 1 is there, that you have to check. 3 comma 1 is there.
Yeah.
Next element, 1 comma 4 is there, whether 4 comma 1 is there, yes it is. 2 comma 2 is there. What about 2 comma 2?
No.
Why not? If you swap 2 and 2, you are getting the same element.
But okay. But there's only 1, 2.
Doesn't matter. See, in the set when you are writing, even if you repeat the element, doesn't make any sense.
Yeah.
So 2 comma 2 is there. Even if you swap 2 comma 2, doesn't matter. It's symmetric.
Okay.
Are you clear? This logic is very,
Okay.
very important. Are you clear with
Okay.
this logic, Aditi?
Yeah. Yeah.
So 1 comma 3 is it. Suppose if I write, even if I write 1 comma 1,
Yeah.
whether it is symmetric? Yes, it is symmetric. So if I write a set like 1 comma 1, 2 comma 2, all the doublets if I write, whether it is symmetric? Yes, it is symmetric.
Okay.
Got it? No.
Yeah.
Yes, it is symmetric. If I swap 1 1, I got 1 1. If I swap 2 2, I got 2 2. If I swap 3 3, I got 3 3. Right?
Okay.
So that means this relation, if I write, if I have written this 1 1 2 2 3 3, it is symmetric as well as reflexive.
Yeah.
It is satisfying both the properties, symmetric as well as reflexive. Clear?
Which one?
I have written just now.
Yeah. Okay.
This is the one I am talking about.
Oh, yeah. That is, yeah.
This is symmetric as well as reflexive. Got the idea?
Yeah.
Clear?
Yeah.
And now let's check the next one. And now check R2. You see this 1 1,
1, 1,
2 2,
2, 2,
3 3,
3,
and
3.
1 3 they have given. Now,
1,
after
3 is
this
not
part,
symmetric.
you see, for 1 3, you
They
didn't
didn't
find the
swap.
3 1. 3 1 is not
Yeah,
there.
they didn't.
If they have attached 3 1 along with that, it would have been symmetric.
Yeah.
Okay, understood.
But they didn't.
But they didn't put the 3 1 there. So that's the reason it's not a symmetric relation. Okay. R1 is symmetric relation because A comma belongs to R1, B comma B belongs to R1. AR1, so this one. R2 is not symmetric because 1 comma 3 belongs to R2, but 3 comma 1 is not there.
Okay. Yeah.
Fine.
3, 1. Yeah.
So this is the logic. It's like strictly you have to stick to this logic.
Yeah.
This logic is very, very important. Hope you understood. Now, let's go ahead. Now, third one. A reflexive relation on set K is not necessarily symmetric. For example, the relation 1, 1, 2, 2, 3, 3, 1, 3 is a reflexive relation.
Yes.
This is a reflexive, definitely reflexive, because all the doublets you can find. No problem.
Yeah.
But the set on the set A, but it is not symmetric. This is what I told you. This is not symmetric. When it will become symmetric?
But 4, 4 is not there, no?
Need not be. I need not give all the elements.
Okay.
You have to check each and every element. See, I need not give all the doublets for you. Suppose 1, 1 I give you, 2, 2 I give you, 3, 3 I give you. Whatever the element I have chosen, I should find the doublet there.
Okay.
I need not take all the 4 elements. Are you getting me? If suppose 4, if I am considering, I should find the doublet of 4. That's why they said subset, subset. That's the concept of subset they're taking. Okay.
But it says it's a reflexive relation on set A 1, 2, 3.
But no. See. I think you are confused once again. Okay, I'll tell you.
No, my question is that like in
Understood.
A there is 1, 2, 3, 4.
Yeah, I understood your question. That's why I'm telling
They have given only 1, 1, 2, 2, 3, 3. 4, 4 is missing.
Yeah, understood. Understood your question. Suppose I want to find A cross A. What is A cross A? Can you tell me?
A cross B, yeah.
A cross A, no. A cross, not A cross B. A cross A. That's it.
A cross A 1, 1.
Yeah.
2, 2.
Yeah.
3, 3. 4, 4.
Next.
And 1, 2.
Yeah.
1, 3.
Yes, good.
1, 4.
Very good. Now, next.
And same 2, 2, 1.
Yeah.
2, 3, 2, 4.
2, 3, 2, 4. Very good. Next.
3, 1, 3, 2, 3, 4.
3, 1, 3, 2, 3, 4. 3, 4. Okay.
4, 1, 4, 2, 4, 3.
4, 1, 4, 2, 4, 3. Anything else?
No.
So we got all the 16 elements? Yes, of course.
Yeah.
You see, 4 are there, n of k into n of a, we got 16, right? Clear?
Yeah.
Now, the relation R is a subset of this A cross A.
Yeah.
When I'm taking subset, I can take any amount of elements I like.
Okay.
I have my own choice. So I will take up to here only.
Oh.
Got the point? Got the point?
Yeah.
So it's not, this relation is made on A. Please understand.
Okay.
This relation is made on A.
Okay.
But I have not considered the element 4.
Okay.
That is my choice. As per my liking, I will do. In fact, the examiner liking, he will do.
Okay.
He will give this condition. And now this is reflexive as well as symmetric. This will satisfy the condition. Reflexive as well as symmetric.
Yeah.
No issues about this. It will satisfy the condition reflexive as well as symmetric. My choice of the relation is just a subset of A cross A. R is, this is the idea. R is a subset of A cross A. I can pick any number of elements I like. I need not worry about taking all the elements.
Okay, got it.
Got the point, right? That's most important.
Yeah.
Right. Now, let's move on. Now, let us see this one. Now, this one you have. So this one, they clearly mentioned that this 1, 3, if you topple 1, 3, 3, 1 should be there for the symmetric. Right. So the 3, 1 is missing here. That's what they are reporting. 3, 1 is missing in the R2. So it's not symmetric. After these elements, they are all symmetric. See,
Okay. Yeah.
up to the three elements, up to these three elements, that is symmetric. Whatever the elements they have considered, they have to check for every element. You have to check for every element. And now this 1, 3, for 1, 3, if you topple, for everything you have to topple and check. So when I swap that 3, 1, that is missing here.
Okay.
So that's the
Yeah.
reason it is not symmetric. Even it fails at one case, that is gone.
Yeah.
One case failure, that is gone. Now let's move. So next is transitive. Transitive. So this is another thing. What is transitive relation? Let A be any set relation A. A is said to be a transitive relation. R on A is said to be a transitive relation. If A comma B belongs to R, B comma C belongs to R, A comma C belongs to R. This is a little bit tough to see. I'll tell you what is it.
Okay.
So I will take an example and I will let you know. So here we go.
Okay.
What does that mean? See, I will write like 1, 3 belongs to a relation. Okay, ma. Next.
Okay.
Another thing, 3, 2 belongs to the same relation.
Okay.
Now, what is transitive means? This 3, whatever is there, it is the transition number. I'll tell you what is it. 1, 3, you write like this. 3, 1, 3, 2, you write like this.
Okay.
This one should match with this.
Okay.
The y coordinate should match with the x coordinate in the two elements. Like that you can remember.
Okay.
Now you remove this. If you remove, you
Okay.
get one thing. 1, 2.
Yeah.
This element also should be present in R. That's called
Okay.
transition. So it is like A is connected to B, B is connected to C, as well as A should be connected to C. That kind of thing. That is called transition.
Okay.
And then you call this as transitive relation.
Okay.
Clear?
Okay.
Got
Yeah,
the
got
point?
it.
Okay, fine.
Yeah.
Now let's move on. So initially it may appear easy or it may appear tough, but you have to manage with that. So next, let's reflexive relation. Okay, now transitive relation we have done. On the set of natural numbers, the relation are defined x is less than y is transitive. Okay, they have written. So natural numbers, they are taken natural numbers. Natural numbers. Natural numbers. What are natural numbers? They start from 1, 2, 3, so
1,
on up
2,
to
3.
infinity.
Yeah.
Now, they say that x less than y is transitive.
1, 2, 3.
Okay, is transitive.
X?
You have to check. You take some element x, you take some element y, you have to show that it is transitive.
X bigger, X smaller than y is
yes, yes. You have to show that it is transitive. So
okay,
for that,
so we can take.
You take some 3 numbers.
Okay.
You choose some 3
1,
numbers.
2, 3.
You can choose 1. A is 1. B is 2.
A is
C is 3. Now you see. Let us check this one. I can write A is less than B, right?
Yeah. A is less than B.
As well as B is less than C. I can write like this.
B is less than C. Yeah.
Can I write A is less than C?
Yeah.
That means what I have done, remove this B and then couple these two.
Yeah.
So that same inequality holds. The beauty is same inequality holds.
Okay.
Inequality holds. So hence we can say that it's a transitive relation. it will take the transition. Got it? No.
Okay.
So suppose for this happens for in fact any kind of real number, that is fine. So if you can do that. A, B, C belongs to R. Suppose any kind of any three real numbers you take. If at all A is less than B and all B is less than C, you can always say that C dominates. It's like A is less than B and less than C. We can write this. You can write this. A is less than B and less than C. That always implies A is less than C.
Yeah.
So that's how it's called a transitive relation, the less than equal. Suppose you consider greater than, that is also transitive. Suppose A is greater than B greater than C. So which implies I can always say that A is greater than C.
Yeah.
If I have this in hand.
Yeah.
So if this happens, I can always say greater than and less than. There are transitive relations for all real numbers. Okay.
Okay.
Now let's move on. So it is like more or less theory, not like problem solving, logic understanding. This is more or less. And now, so they have written that you can see that X is transitive. We have done. So X is related to Y is related to Z, X is related to Z. Then you can say that it is a transitive relation. Then it is a transitive relation. Okay. Now take an example. Let A is set of straight lines in a plane. Then the relation is parallel to on A is a transitive relation because L1 L2 is a beautiful example. Okay, I will tell you what is this.
Okay.
Suppose we do this. Now we'll do a small exercise. What is the set of lines in a plane? So let us draw one big plane like this. Okay. This is the plane we consider. And now let's draw some straight lines. This is a straight line 1. Okay. This is straight line 2. This is straight line 3. And this is the set what they're talking about. Okay. This is straight line 4. This is the straight line 5. And now this is the straight line 6. Let us draw 6 straight lines. So what does this mean? Okay, let us mark this as A, straight line A, straight line B, straight line C, straight line D, straight line E, and straight line F. Let us say.
Okay.
Now what does this mean? What they're telling? So can I write A is parallel to B?
Yeah.
Yes, because straight lines, these two straight lines are parallel. Okay, consider all A, B, C, D, E, F. They're all parallel straight lines.
Okay.
And I can write B is parallel to C.
Yeah.
Now, can I write A is parallel to C? Because these are all, you can see that these are straight lines, both are parallel. So I can write A is parallel to C from this. Of course, can I transmit this idea everywhere?
Yeah.
Yeah, of course, because A is parallel to B, B is parallel to C, C is parallel to D, that means A is parallel to D.
Yeah.
And now, similarly, D is parallel to E and E is parallel to F. So instead of A, B, C, D, they said this is L1, this is L2, this is L3, like that. Line 1, line 2, line 3, line 4, line 5, line 6. Like this, they told.
Yeah.
So L1 is parallel to L2, L2 is parallel to L3, L3 is parallel to L4. That means L1 is parallel to L4. You can always say that. Clear?
Yeah.
Okay. Now this is the example what they have told us. Now let's move on to the next one. So set of straight lines in a plane is what they have spoken. Now that is the transitive relation what they have spoken to us. Now let us see the next case. Check the relation for reflexivity, symmetry, and transitivity where R is defined as L1 related to L2 if and only if to L2 if and only if L1 is perpendicular to L2 for all L1, L2 belongs to A. Where R is defined as L1 related to R2, L1 is perpendicular to L2. This is what they told.
Okay.
Now, let us see.
L1 related to L2.
You don't have to write. Just check. Let's see this here.
L1 is related to L2. If L1 is
perpendicular to each other. That means the situation they are talking about is the perpendicular lines.
Perpendicular.
L1 is perpendicular to L2.
To L2
Now,
for all L1, L2 belongs to A.
Yes.
Check the relation or reflexive. Or is.
So the relation they have considered is that it contains all the lines which are mutually perpendicular to each other.
Okay.
That's how they have taken.
Okay.
This is very interesting.
L1 is perpendicular to L2. And L1, L2 belongs to A.
Yes. Yeah.
Check the reflectivity.
Whether they are reflective or not.
If double.
You don't find a doublet here. How do you check the reflectivity? Here, reflectivity means that is in numbers. See, reflectivity means if L1 is perpendicular to L2, suppose I consider it like this. L1 is perpendicular to L2. Can I write L2 perpendicular to L1?
No.
Why? Why, ma? Why do you think so?
Yeah, you can. Yeah, you can.
So what does this mean?
L1 is perpendicular to L2. L2 is perpendicular to
L1. What does this mean?
L1.
What does this mean? It is symmetric.
Symmetric.
No.
Symmetric. Yeah, can be symmetric.
Now reflexivity will not work. Why? If you consider doublet, L1 cannot be perpendicular to the same line.
Same line. Okay.
Right? If you take a line, that line cannot be perpendicular to itself.
Go to the same line.
Yeah.
Okay.
That if you consider a line, it cannot be perpendicular to itself.
Yeah. Okay.
So here,
that
is broken. So here you can get the symmetry.
Symmetry, yeah.
You can get. Right. L1 perpendicular to L2 means L2 perpendicular to L1. That symmetry you will get.
Yeah.
So
but
you have, it is not transitive. Why it is not transitive?
Because L1 cannot be L1 bigger than that doesn't make sense.
Not bigger. Bigger or smaller is not the case. Here it is a question of geometry. Nothing like bigger or smaller. You see this. Now how to check the transitivity? You had, for checking transitivity, you need 3 lines here. L1, L2, L3. 3 lines here.
There is no L3.
You have to take 3 lines. Why do you think the L3 is not there?
Okay.
You have as many lines as you want.
Yeah,
I give you as many lines as you want. Why not? You can take L3.
Okay.
No problem. You take as many lines as you want. And then I wanted to check this. Where do you find a doublet? L1 cannot be perpendicular to L1. Right?
Yeah.
So the doublet is missing. So that's the reason you don't have the reflexivity. 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 I am talking about reflexivity. So you cannot find a doublet in this. Because any line cannot be perpendicular to itself.
Its own self. Okay.
Yeah. So the reflexivity is gone. Now, when you consider the symmetry, suppose you consider L1 perpendicular to L2, then L2 is perpendicular to L1. So when you topple both, such elements you can find.
Okay.
For transitivity, you have to take 3 elements. Remember this. For transitivity, you have to check 3 elements. Now, for transitive, let's write this. L1 is perpendicular to L2.
Yeah.
Now, let us draw that. L1 is this. L2 is like this. This is a geometry problem. Think carefully. L2, right? And now, I write the second situation. L2 is perpendicular to L3. Right? L2 is perpendicular to L3. That means I have to draw like this only, right? This is the only way.
Yeah.
In a plane. L2 is perpendicular to L3. Now, this is my L3. Now, can I write L1 is perpendicular to L3? Think.
No.
No, because L1 becomes parallel to L3.
Yeah.
Got it? No.
Parallel, yeah.
L1 becomes parallel to L3, which means that the transitivity is broken.
Yeah, okay.
Understood?
Yeah.
So that is what they want to check.
Okay.
Next. Clear? Can I clear this?
Yeah.
Okay. Now, let us see the next part. So here we go. Equivalence relation. Reflexive, symmetric, transitive. All the 3 are there within that. Then it is called an equivalence relation. Simple. Reflexive, symmetric, transitive. All the 3 you can find within the same thing.
Okay.
Then you will find it is equivalence relation. Simple.
Okay.
So you see that a relation R on the set A is an equivalence relation on A if and only if it is reflexive. That is, you can find all the doublets.
Reflective, reflexive, symmetric.
Symmetric. A comma belongs to R and B comma A belongs to R.
And transitive.
And transitive. All the 3 properties works for every element what is chosen.
Okay.
It works for every element, whatever the element you take. It works for everything. That means you will find all the doublets.
Okay.
You will find everything. You will find all the doublets. You will find the toppling things. You will find everything. Okay.
Okay.
Clear. Now let's move on.
Yeah.
We have an example here. Congruent triangles. Is it an equivalence relation or not? Congruent triangles. Is it an equivalence relation or not? We have to check that. They asked congruence of triangles.
Congruence.
Congruence. What is congruence?
Okay.
When do you say 2 triangles are congruent?
Congruence. When it's equivalent. No.
So what is congruent triangle, Santi?
Congruence triangle.
Congruent triangle is what?
When their correspondings are
very
equal.
Good. No, when the corresponding angles are equal, also
sides.
Then you will say the triangles are congruent.
Yeah.
The corresponding angles.
But they don't they say another something else also they say.
No, I didn't get you.
And there's another word for this when sides of a triangle and angles.
That is called congruent.
And length.
There are another thing called similar triangles.
Okay.
Similar triangles means only angles are equal.
Oh yeah.
That is called similar. Congruence means sides are equal,
Side
angles are also equal.
equal.
So that is called congruent triangles.
Yeah.
Similar triangles means only
Singular
angles are equal.
triangles, only angles are equal.
Only angles.
Yeah, angles.
Only if the angles are equal, then you will say similar triangle.
Single.
If sides are equal, angles are also equal, then you will say that
Yeah.
the triangles are congruent.
Congruent.
Clear? And now
Yeah.
that means in this particular set, you are taking the photographs of the same triangle. Suppose you draw one triangle. You take a
And the
photograph.
same triangle.
Simple. I will tell you. Imagine this. You take a triangle. You draw the triangle.
Yeah.
You took a photograph.
And then the same triangle.
You take a photograph of that.
Yeah.
You take a photograph.
Yeah.
And put multiple photographs of the same triangle in your Facebook. Imagine your Facebook is the same.
Okay.
So when you do that, what happens if the triangle is same?
Yeah, it's the same triangle.
So can I find doublets?
Yeah.
Can I find symmetry?
Symmetry.
Of course.
Yeah.
Why not? You are taking same photograph, na? Multiple
Yeah.
photographs. Can I find transitive?
Yeah.
Yeah, of course. That's the equivalence relation.
Yeah.
So that's what is written. It is reflexive because one triangle is congruent to other triangle. Triangle 1 is congruent to triangle 2. Photograph 1 is same as photograph 2. Which means photograph 2 is same as photograph 1.
Yeah.
That means I got a doublet. Now,
yeah.
The photograph 1 and photograph 2 are looking alike.
Photograph 1 and photograph 2, yeah.
Are looking alike. If you swap it, whether it is there within the set, of course it is there. And now
So
the third thing is also same. Triangle 1 is congruent to triangle 2. Triangle 2 is congruent to triangle 3. You have triangle 1 is congruent to triangle 3.
Yeah. Okay.
So that's why it's an equivalence relation.
Okay.
Clear?
Yeah.
Let's move on.
Okay.
Show that the relation R defined on the set A of all triangles in a plane of all triangles in a plane as R is equal to T1 comma T2. Set A of all triangles in a plane as R is equal to T1 comma T2. T1 is similar to T2. Is an equivalence relation or not?
T1 is
similar to T2. Similar triangles.
Okay.
I just told you about similar triangles. Corresponding angles are equal.
Corresponding equivalence, yeah.
Suppose you consider, can I find doublets?
Yeah.
Of course. Why? T1 is similar to T1.
Yeah.
So you will find doublets.
And we can find symmetry also.
Definitely. And you can find transition also.
Yeah.
Right.
It is like, yeah, just the last.
Yeah. So you can find the transition also. Because T1 is similar to T2. T2 is similar to T3.
Yeah.
Definitely T1 is similar to T3.
Yep.
Clear?
Yeah.
Now let's see the progress. Check your progress. Clear up to now?
Yeah.
Now let us solve the first problem. Let R be a relation on the set of all the lines in a plane defined by L1, L2 belongs to R. Line L1 is parallel to L2. So the same thing, we just solved this. So I can try it for yourself.
Yeah.
Easy,
L1,
right? So how do you write this about
L1, L2 belongs to R, which line is parallel to line L1 is parallel
to L2.
Parallel to L2. Show that
it's an equivalence relation.
Equivalence relation.
We just solved this.
L1 is parallel to
L1.
Yeah.
For
so it is reflexive.
Yeah, definitely. You can find all the doublets because L1 can be parallel to L1.
L1 is parallel
to
L1. So it is reflexive. And we can swap it also.
Yeah, of course. Of course, you can swap and see.
Yeah. See, if you swap and see, right, L1 is parallel to
L2. The relation holds.
Yeah. So it is symmetric.
Obviously. Transitive.
Yeah. So L1 is parallel to L2. So
transitive means 3 lines you have to take.
3 lines, yeah. So L1 is parallel to L2. And L1 is parallel to L3.
L1 is parallel to L2. L2 is parallel to L3.
L2 is parallel to L3. And L1 is parallel, has to be parallel to L3.
That's it.
So it's transitive.
So it is transitive.
Yeah.
Clear?
Yeah. L2 is parallel to L3 and L1 is parallel to L3. Yeah.
Rama. Now let us see next question.
Show that the relation R
on set A
on the set of
a point in a plane
given by R is equal to
P comma Q.
PQ. Distance of the point P
from
the origin is the
same as distance of the point Q from origin. Is an equivalence relation.
Well said.
So how do you do that?
Show that R on the set of a plane is given by R is equal to PQ distance of the point P from the origin is P. This distance is the same. Should I show that it's an equivalence?
Yeah, you have
relation?
to show that it's an equivalence relation. Yes.
Okay. So reflex. You can double it, so it's you can write PP and QQ.
Yes. Why it is on the double it? Why do you feel it's a double it?
You can double it and it will become so it is a reflective relation.
No, Aditi, you are not answered yet.
Yeah.
Why do you think that it is a double it?
Because it has the same distance from the origin. Of X.
I didn't get the X part.
P to, for example, P to X and Q to X has the same.
Can you draw and show me? Can you draw and show me? Is it possible?
Okay.
Yeah. Yeah. I want you to understand concepts. So the reason I'm asking this.
Okay.
Yeah, I tell you.
Wait, where is the?
Yeah, I tell you. This is the origin, okay?
Yeah, like this.
Now you
And
take
then
the
this
point.
is like,
Yeah, good. Yeah, you are doing it. Yeah, fine. Origin.
and it is
You
from
mark
here.
some
It
point
is
here.
P,
Yeah. Yeah. Yeah, this is P. So
and
what
this
they are
is the
looking for
same.
this distance R, right?
Yeah,
They are looking for this
this,
distance R. Now,
this distance is same
whether
as
if whether OP is equal to OP, that's all you have to tell.
OP is equal to OP. Yeah.
Yeah, that's why you get the double A.
Okay.
This is the
And
point you have
OQ
to
is
make.
equal to OQ.
Yeah, of course. For every point that they ask the distance of the point from origin.
Okay.
So OP is equal to OP, OQ is equal to OQ. You can always find the doublets. No problem. And now you tell me the next one.
Next, symmetric. It can also be symmetric. OP, PO.
No, not that way.
Symmetric means when you
No.
reverse it.
No. I expected it. No, not that way. Think once again.
Okay. From the distance, OP is same as this. So OP is equal to OP.
OP is equal
And
to OP.
OQ
We
is
have done already.
Yeah. Then it is symmetric also, no?
Only
No.
that coordinate is symmetric.
That coordinate is symmetric. Symmetric means when it is.
You have to take like x comma y.
Oh. So x.
You take p comma q. You are given p comma q, right?
Yeah,
if you take p comma q, if you take p comma q, whether q comma p exists there.
Yeah.
That's all you have to tell.
Okay. So p comma p. What is this?
What is p refers to?
P.
That's you have to understand. What is p refers to?
Yeah. So p comma q. P and Q. You can ulta this QP.
You ulta it whether it is existing in that or not. That you have to tell me. Why? Why it
It's existing.
Why?
It is existing because OP and OQ has the same distance.
Yeah.
And it is reflected.
Yeah, that's what you have to bring in. It is existing because OP is equal to OQ.
Yeah. OP is equal to OQ.
OQ. That you have to bring in. That is the point you have to bring in. Because OP is equal to OQ, this will exist. Even if you topple, the distances are not changing. So here P refers to the distance OP.
Yeah.
Q refers to the distance OQ.
Yeah. Okay.
Hope you got it.
Yeah.
Now go for the third.
Okay.
Now you have to take PQ or 3 points.
Third one. Okay.
Now, as per the condition, OP is equal to OQ is equal to OR, right?
OP is equal to
OQ is equal to OR. They have given that already.
Yeah.
Right.
So it is a transitive.
Yeah, it is transitive. So it is. So finally, what is the conclusion? Final conclusion.
OP is equal to OQ is equal to OR.
Okay, ma, transitive. After that, what you will write?
And then OP is equal. 1 second. OP is equal to OQ is equal to OR. So O is,
Look at the question. Look at the question. What you have to prove?
if it's transitive,
No, look at the question once again. Please read the question.
show that the relation R on the set A of points in a plane given by R is equal to PQ. Distance of the point from the origin is same as the distance of the point Q from the origin is an equivalence
You have
relation.
tell that no at the end. That's what I'm asking. What you have to do at the end?
That it is a equivalence reaction.
Reaction.
Relation, sorry.
Oh my God.
Equivalence relation.
You're not reading chemistry, we're reading mathematics. Where is reaction coming? I was thinking. It's an equivalence relation. Okay. So what you will write at the end? Reflexive, symmetric, transitive, all the things you will write. At the end, you have to write that since all the three are satisfied, this is an equivalence relation.
Yeah, equivalence relation.
Okay, not reaction, it's a relation. No chemistry here, only maths.
Yeah.
Next one.
Okay.
Show that each relation R in the set.
Show that each relation in the set
A is equal to x belongs to Z. 0 less than x less than 12. This I will do. This will do tomorrow.
Okay.
Don't worry.
Okay.
Here we'll stop. This will do tomorrow.
Yeah. Okay.
We'll take a break. Amma, tomorrow what time you are available?
Tomorrow.
Same time?
Again, same time?
Yeah, it's okay.
Yeah.
We'll do it at the same time.
Yeah, okay.
We'll
Okay.
No problem.
Okay. Or we can do it in the morning.
Morning. I am a bit busy during the time.
Okay.
So around I am available at 3 p.m. France time onwards.
3 p.m. we can do. 3 p.m.
3 p.m. we can do. Around 2:30 also is okay. 2:30 is also okay. 2:30 France time. 2:30 around 2:30, 2 o'clock, 2:30 France time. I am fine. I'll intimate you.
Actually, my tennis class gets over at 2:30. It's like 2:45 is also good.
2:45 we can start. No issues.
Okay.
2:45 or 3 around we can start. Okay, ma.
Okay. Thank
Take
you.
care.
Bye-bye.
Bye.
Good night.
Good night. Bye.